Well, hello, welcome again to our journey into linear algebra. We've been looking at applications of symmetric matrices, and we looked at 2 dimensions and 3 dimensions. And I wanted now to say something briefly about this amazing law called Sylvester's law of inertia. So the motivation of this is that although we're guaranteed the eigenvalues of a real symmetric matrix are real, I should really have the word real in here, they may be rather hard to calculate. You end up with a cubic, even in the 3 by 3 case, and that can be difficult to solve. And in many applications, we're really only interested in the signs of the eigenvalues and not necessarily the values themselves. Now we can find the signs, as I will show you shortly, of the eigenvalues by completing the squares and relying on the following lovely and very surprising theorem called Sylvester's law of inertia, which says you take an n by n symmetric matrix and you put x to be this vector here, then if the expression that can be written as a sum of multiples of squares of independent linear combinations of these x's, then the number of positive, negative and 0 multiples is always the same. So the number of the positive, negative and 0 multiples of these sums of squares correspond to the signs of the eigenvalues. So let me do an example to show you how nice this is. So we're going to take this matrix A, which is the matrix -1, -4, -8. And we want to find out what the signs of the eigenvalues are without actually calculating the eigenvalues themselves, which you might like to try. In this case is not particularly nice, I think. So we look at the corresponding conic or quadric form or expression for this. So looking at the main diagonal, we get an x squared, we get a 2y squared, there's no z squareds. Now the xy term comes from these two, so there's going to be a -8xy. The xz term comes from these two, so that's -16xz. And the yz term comes from these two, so that's 8yz. Now what we do is we start to complete the square on this, much in the same way as you did at high school with quadratics, except now we've got more variables. So I concentrate firstly on the x terms. So I'm going to write down an x, so that I'm going to write something in here all squared. So an x, that will square out to give me x squared. Now as with completing the square, you take half the coefficient. So half of -8y is -4y. We plonk that in there. And half of -16z is -8z. And we're going to imagine squaring all this out. Now if we square it all out, we'll get an x squared, that's what we had here. We're going to get we'll get twice the product of these two, that gives me this. We'll get twice the product of these two, gives me this. We're also going to get this squared, so I'm going to get a 16 y squared, but I only had a 2y squared up here, so I better subtract off 14y squared. I'm going to get this squared, which is 64z squared. There were no z squareds here, so I better subtract off 64z squared. And also I'm going to get twice the product of these two, so the two minuses will give me a plus. I'll get 8 fours are 32 times 2 is, so I'll get a plus 64yz, and I have to subtract off the 64yz. So you might just check carefully that you understand all those bits of algebra there. The point is now, at this stage, these terms here have no x's in them. Now what I'm going to do, I just factor a minus out of this, and I'm going to put this term first because it's got a square in it, it's a bit easier. You could also factor out the 64, that would give you fractions here. I don't like working with fractions, but you could do that. You could factor out the 64 and have fractions in here to complete the square on, and you'll get lots of fractions in fact. So instead of that, I'm going to just complete the square on the z here. I'm going to think, well, this thing here is 8z all squared, so I'm going to write this as 8z. Now I've got to put plus something y. At the moment I've got a 64yz. If I multiply these together I get 32 and double it. then that will give me exactly this. So if I put a 4 there, then that will work. So what I've done there is essentially I've said I want 8 times something to give me half of this, so 8 fours are 32. Now looking inside the brackets here, when I expand this out, I'm going to get 16y squared, and I only wanted 14, so I've got to subtract off 2y squared. And that's it. So now I just take the brackets back out again, and I've got this expression squared minus this expression squared plus 2y squared here. Now this is not giving me the eigenvalues, but it's giving me the signs of the eigenvalues. That's what Sylvester's law tells me. So I've got a plus here, a minus, and a plus here. So there'll be 2 positive and 1 negative eigenvalues. 2 positive and 1 negative eigenvalues. Well, you might like to try, here's another one here, you might like to try this one yourself, but then I'll compare it with my solution. So I want to find the signs of the eigenvalues of this matrix and identify this surface here. X transpose AX is 1. So you might like to halt the video at this point, have a go at doing this one yourself, and then compare it with my solution. And here is the worked solution to this. There's our matrix here. And again, I'm going to write down the corresponding quadratic expression. So I'm going to get an x squared, a 4y squared, a 6z squared. I get a 4xy, a 6xz, and a 6yz. Now, completing the square on the x's, I look at this term, and this term. Halve the coefficients. So I get an x plus I get 2y and 3z, and then you imagine what happens if I expanded out this square. I'll get an x squared, I'll get twice the product of these, I'll get twice the product of these. I pick up a 4y squared, well that was already there, so I don't need to do anything with that one. I pick up a 9z squared, I only had 6 here, so I better subtract 3. And I pick up a 3 2s are 6, that's 12. YZ, I only had 6 here, so I've got to subtract off 6. Now again, I'm going to factor a minus out. I'm going to factor a minus 3 out of this, in fact. This one's fairly easy. Factor out a minus 3 and then complete the square inside here. So you halve the coefficient, you'll get a y. And then when you expand this out, you'll get z squared plus 2yz plus y squared. So I need to subtract off a y squared. And take the brackets out of this, gives me this here. And so I have 2 positive and 1 negative eigenvalue. So if we now look at x transpose A, x is 1, then this will correspond to a conic which has got 2 positive and 1 negative eigenvalues. So this again will be a hyperboloid of one sheet. Now beware, the eigenvalues are not 1 minus 3, 3. We don't know what they are. They're horrible numbers, but it's their signs that we get from this completing of the square method. Final example here. We want to find the eigenvalues of this, and again identify these 2 surfaces. Again, you might like to halt the video and try this one yourself now and compare it with what I get. But here is the worked solution to this. So we get 1 minus 2, 2, minus 2, 5, minus 1, 2, minus 1, 13. Again, the corresponding quadratic form now is x squared plus 5y squared plus 13z squared. I get minus 4xz, I get plus xy, plus 4xz and minus 2yz. And we complete the square on the x terms. So I halve the coefficients, expand it back out again. I'm going to get these terms are all fine. I'll get a 4y squared. I had a 5 up here, so I better add 1 in. I get a 4z squared, but I had a 13 here, so I better add 9 on. and I get a minus 2 2s, 4 2s, 8, so I get a minus 8, and I wanted minus 2, so I better add 6 on. And this one here, in fact, is a perfect square, so I can just write this squared plus this squared. Now this tells me that there are two positive eigenvalues, and one of the eigenvalues is 0. And by the way, that means then that the determinant of this matrix is 0, and I'll leave you to check that. You can check this determinant of this matrix is indeed 0, so that confirms that lambda equals 0 was one of the eigenvalues in this case. Now, if we put this conic, use this matrix to form this conic, x transpose AX is 1, then we're going to have a cylinder. It's not clear whether it's a circular or elliptic cylinder. We don't know what the eigenvalues are, just their signs. But we're either going to get a circular or an elliptic cylinder. And if I have this equal to minus 1, well, you can't have the sum of two squares being minus 1, so in this case that would not exist. And little challenge problem, this is really quite difficult, but you might like to try this one. Try completing the square on, this is a bit of an old saw, this one. Try completing the square on this one and see how you go. This is quite difficult to do, in fact, but that's a nice exercise. And that's the end of the chapter on the applications of symmetric matrices.